Okay, so this is our last class session. We're going to talk about multiple regression and chi-square test. Chi-square test kind of doesn't fit in with the rest of the stuff, so we're going to look at it last, but it's useful for when you have qualitative variables. But in the meantime, we're going to focus on interpreting the printout from what software will give you for multiple regression and trying to identify each part of it and what's kind of important. We talked a little bit about it last week with simple linear regression, but in general, you use more than one variable to try to explain some phenomenon when you're building a model. So, all right, so we'll get started. So chapter 12, multiple regression. This is going to be part of, inferential statistics, but so statistical inference, up to now we have been doing data analysis describing the nearest linear relationship between the observed data x and y in simple linear regression, so just one x and one y. Now we're going to shift our point of view and regard the 92 students as a sample of the population of students at large and try to determine what we might be able to infer from that. Typical regression model for the whole population is the linear relationship of y, some dependent random variable, plus, in this case, alpha is our y-intercept, and beta is our coefficient for x. And then there's some error associated with the, the sampling process or any other kind of bias that might have been in there, or all the other x values that are not included. So y is the dependent variable, x is the independent variable, which may or may not be random, and alpha and beta are the unknown parameters we seek to estimate, and epsilon, or small e, represents random error fluctuations. So for the height versus weight model that we talked about last week, y was the height and x, or y was the weight and x is the height, and alpha and beta are unknown, and you can think of them as some random component of the weights and heights of the students. So the error term is kind of that distribution about the line. That's kind of what this is trying to say. So the distribution of the error term is in fact different for different values of x. 5-foot people or 5-footers vary less in their height than 6-foot people. But nevertheless, we now make simplifying assumptions. Let's suppose that for all values of x, the errors are independent, normal, and have the same standard deviation. Basically, that gets shortened down into something called IID, independent, identically distributed. It's kind of one of the assumptions that allow us to do linear regression. So in reality, those distributions may kind of differ along the way. That's a complicated problem to solve. That's in a much higher level of statistics. But for our case, we're going to make an assumption that, and simplify it, that the error term is distributed normally about our linear regression line. It just makes things go a little smoother at these kind of lower level models. So one possible problem is some of those little toddlers must weigh less than nothing, right? So what do we do about instances when values are below 0, especially when in an applied world like height and weight? So maybe the weight model might be y equals -125 plus 4x plus the error term. So the error term is normal with mean 0 and standard deviation 15 pounds. And according to this model, students who are 6'4" or 76 inches have the distribution of -125 plus 4 times 76 plus the error term, so 175 plus some margin of error. So for x equals 76, y is normal with mean 175 and standard deviation 15 pounds. So somebody that is, how did he say, 6'4", roughly within 2 standard deviations should be between 160 and 190 pounds. So now given the model y equals alpha plus beta x plus the error term, we want to do, as we've done repeatedly in the last few chapters, take a sample and use it to estimate alpha and beta. So one can show that the alpha and beta we got by the least squares method are blue, the best linear unbiased estimators of alpha and beta. So basically that means what it means. Linear regression is trying to find the best linear unbiased estimator because we're taking estimates of alpha and beta, right? And we want to kind of minimize those errors. So we have our model line, we have the regression line that we fit to the data, and then we want to find that best line. But as usual, different samples yield different collections of data, which generate different regression lines. So these lines are distributed around the line y equals alpha plus beta x plus the error term. Our question becomes, how are alpha and beta distributed around, or how are A and B, what we estimate for alpha and beta respectively, and how do we construct confidence intervals and test hypotheses? So for each data point, x sub I and y sub I, we have y sub I equals a plus b xi plus ei. So these are our estimates for a and b, or the y-intercept and the coefficient for x. So, and e is our error term that we're going to estimate as well. So e, or the error term, is equal to yi minus our point estimator for y, is the y distance of y from the regression line, how much error is in that particular sample. So the ei are sample values of the error term, and they give us estimator s, or sigma of the error term, the standard deviation of the error term, is given here. So standard deviation for that is given as the square root of the sum of the error term squared divided by n minus 2. So that's the sample size minus 2. So why n minus 2 in the denominator? Because we have used up 2 degrees of freedom to compute a and b, leaving n minus 2. So because we're trying to estimate a and a b, that's where the 2 comes from. Oops. So although it is obvious, we can also write s as difference of squares, the sum of squares of y, minus b times the sum of squares of xy, and minus 2, still 2 degrees of freedom. So formula which allows us to compute s directly from the sample statistics. So to repeat, s is an estimator of how widely data points will be scattered around the line. So that's the standard deviation about the regression line. So confidence intervals, we're going to compute 95% confidence interval for alpha and beta. Have the the familiar form. We have beta equals our point estimate b plus or minus. So it's 95%. So alpha 0.05 divided by 2 gives us the 0.025. We look that up on our t-value chart, and then we multiply that times the standard error of b, and that gives us the confidence interval. So the same way we find a confidence interval in general. And you can do that for both the coefficient for x's, which would be what the betas are. Here, this particular book uses alpha, but it could be beta 0 for the intercept. So this is where we use the t-distribution with n minus 2 degrees of freedom when we're looking it up. But a lot of these values will be printed out from using software. So we're going to focus more on how to interpret data from our information from a printout. All right, so the standard errors, however, look rather unfamiliar. They are without deviation for calculating those two out. So what happened to our precious 1 divided by square root of n when we were trying to compensate for our sample size? Well, it was replaced by the sum of squares of the x's. So like n, the sum of squares of x's increases as we add more data points, but it also reflects the total spread of the x data. For example, if all students sampled had the same height, we would be unjustified in drawing any conclusion about the dependence of weight on height. In that case, the sum of squares for the x's would be 0, giving b infinity and infinitely wide confidence intervals. Basically, that's what that's saying. We would have an infinite line going up for height if we had just one weight or one height. So how well can we predict the mean response y at a fixed value of x naught? So for instance, what is the mean weight of students of height 76 inches with a 95% confidence interval? This is where you get these Bollinger Bands. So you can see, the error decreases as we get to the mean, but that's kind of what those are entailing. Let's see. So suppose a new student enrolls who has a height of some new x value. How well can we predict the new height without measuring it? So if we look within our 95% prediction interval, based on our confidence interval, for a new individual y new with observed x new is y new equals a plus bx new plus or minus our t value for 0.025 corresponding to 95% times the standard error of y new. And that gives us this equation. But we shouldn't have to calculate that out manually, so don't worry about it too much right now. So both these standard errors contain a term that grows larger as the x value, x0 or x new, gets farther from the mean. That's what I was saying with these kind of Bollinger Bands. So the further we get away, we can see that more error is being introduced because we're basing it around, standard error of a particular mean that we're taking. So that's why this shape is the way it is. Basically, if you wiggle the regression line, it makes more of a difference farther from the mean. Remember, the line always passes through the mean x, y, and x bar and y bar. So let's work it out for the rig data. For the mean weight when x equals 76 inches, we have b equals -200 and a equals 5. Then I can put that in, y equals -200 plus 5 times 76 plus or minus 2.365, which is the t value, 25.15 being the standard error. So we simplify that and we get at 76 inches, 180 pounds plus or minus 36.34. So the estimated mean of a 6'4" student is 180 pounds, and we're 95% confident that we're within 36 pounds of the true mean. So for our new student, who is 6'4", we use our rigged sample of 9 points to predict that. But then, you can see how poorly this gets. 180 plus or minus 70 pounds. There's a pretty big difference between somebody who's 110 pounds and 180 pounds, or 180 pounds and 250 pounds. So it's a pretty wide confidence interval. So the intervals are pretty terrible. What's the problem? There are two problems. Height alone is not a very good predictor of weight. There's effect of gender and genetics. 9 data points weren't enough in particular. There was only one student with height 76 inches. For most statistical problems, you're going to want a sample size of at least 30. But for most real world applications of statistics, you're going to want a sample size of at least 200. So using 9 was kind of not a particularly good idea, but it's a little easier to visualize points. All right, so the Penn State students give better estimates. So now we have a higher sample size, and we can look at creating a better model, a better line to fit. All right, so hypothesis testing. We talked a little bit about this also last week. The complete skeptic might suggest that there is no relationship between height and weight. That would mean that the slope of the line was 0, right? So x has no effect on y because regardless of the weight, it would always be the same height. So we take that as the null hypothesis. So h null, or h0, is beta equals 0, and thus, in that case, the test statistic t would be our estimated beta value b divided by the standard error of that, and that'll give us our t statistic that we would compare to our t critical value, or we'll use p values based on this t stat. So it has the t-distribution with n minus 2 degrees of freedom. As usual, the significance test depends on the alternate hypothesis. So, I mean, if we're looking at a right-tailed test, beta would be greater than 0. Left-tailed test, beta would be less than 0. And there's also, beta does not equal 0, which would be a two-tailed test. For the rigged weight data, we strongly suspect that the alternate hypothesis should be beta is greater than 0. So typically you're going to use a two-tailed test unless you either you have a strong idea of the direction that the relationship is. But when you use a two-tailed test, you divide that alpha level up into two tails. You're making that area that you have to exceed to get a significant test smaller. So at least in more scientific studies and even science, you'll see a lot of test unless you have a strong reason to believe that it is a greater than or less than type hypothesis. That's something to note, possibly for a future class or something. Anyhow, so the alternative hypothesis for this particular example is beta is greater than 0. So we test that. T observed, we have 5 divided by 1.62 at standard error, we get 3.08. For 7 degrees of freedom, T.05 equals 1.895. Since the T observed is greater than T.05, we reject the null hypothesis at the alpha equals 0.05. Significance level. Include that there is a significant positive relationship between height and weight. I guess in this example, the taller somebody is, the more they probably weigh. So that would be an instance where you could use a directional hypothesis. But like I said, a lot of times in business, it usually falls under social science, and you're going to end up with more two-tailed tests, which would be beta does not equal 0. All right. So, multiple linear regression. We can use the same basic ideas to analyze relationships between a dependent variable and several independent variables. So that's kind of what we've been getting at, right? Weight and height. There's more to that relationship, particularly age, sex, diet, body type, etc. So we can look at what different each, say, x1 is age, and x2 is sex, and x3 is diet, x4 is body, etc. So we'd want to find out what each of those coefficients were, and that would, we would learn more about the particular problem. And from an r-squared standpoint, our r-squared would go up, not only because we're adding variables, but we'd be explaining more of that variation. And so there's just more to learn about the variable y than just using one variable such as height or weight. So we're not going to really talk too much about nonlinear regression in this class, but there is one question about sometimes the data is not linear. Most of the time the data is not linear. So then it would be nonlinear, and you could set up a polynomial type regression like x1 or x squared makes it, now polynomial instead of just linear. But something just to note, like this would be a concave facing downward curve, a parabola shape, as opposed to, or it's a quadratic function instead of a linear function. But I'm not going to say anything more really than that. Those are more advanced classes that you would learn about nonlinear regression. One important one, though, that you may want to look into one day is logistic regression, and that's when you have a binary dependent variable. If you take econometrics or another advanced class, we get more into those kinds of models, but just know they exist and not everything's linear, basically. Okay, so regression diagnostics. Fitting a complex model to data can obscure many difficulties. We use regression diagnostic procedures to uncover any lurking nasty surprises. So, simplest procedure is to plot the results or the errors against the predictor y. So you'll sometimes hear people talking about residuals when they're talking about regression. So remember the error or epsilon is assumed to be independent of x. So what we would expect is the residuals to be, completely randomly distributed about y, right? So there's no r. So the error term is independent of x. So any pattern in the residuals indicates a definite problem with the model assumptions. And if you ended up with something like this, and there was, something called homoscedasticity or heteroscedasticity, or where there's different functions about the error term and the dependent variables, there's more advanced versions of regression that we can utilize to kind of compensate for that. Or there's another problem called simultaneous causality. But those are all a lot more advanced problems than we're going to really talk about in this class. But okay, well, we talk a little bit about here, but we won't talk about really how to overcome it here. So a typical lurking nasty surprise exists in the height-weight data. It's called heteroscedastic, which basically means that as y increases, the error becomes more spread out, or the error gets larger the higher the y value. And then you'll see this typical kind of like funnel-shaped pattern in the residuals for heteroscedastic data. And actually, this is more common in business type research or models because in any sort of science. So it's a problem, but not something you're going to overcome just yet. Okay, so talked about some important kind of terminology and definitions, but now let's look at how do you interpret some output. So we're given this model. If you had put in some data and you run regression in Excel or SPSS or SAS or R, you'll get this kind of data spit out. And what you need to do is understand how to interpret it. So we'll look at the different values here. So what are the sample estimates of like beta 0? So beta 0 is our intercept, and when you get your output, you can either look at the regression line if you're given it. You can see the y-intercept is here, 1,774.75, or it's in this column of coefficients. So our beta 0 is here, 1,774.75. Our beta 1 and beta 2 are our coefficients for x1 and x2 variable. So beta 1 is negative 551.67, and beta 2 is negative 335.08, and you can see those as the coefficients in our regression line. So typically when you have a regression, you're going to have an ANOVA as well, so analysis of variance. So some important values that you may need are the sum of squared errors. So if you look, you have your regression, you have your residual error or just error, and you have your total. So this would be your SSR, your sum of squared regressions, and here would be your sum of squared error. So find SSE, the SSE would be 664,979, and our mean sum of squared error would be in this column. So 39,116. And S, our standard deviation of our regression model is here. S equals 197.779. Okay, so what is 2 standard deviations? Well, it would be 2 times this number, so 2 times 197.179. So 2 standard deviations would be 395.558 plus or minus. Okay. I wanted to test the null hypothesis of beta 1 equals against the alternative that beta 1 does not equal 0. So that's a two-tailed test, which should be given default here. And we have an alpha value of 0.01. Well, it's given to us in the output here. So we're given the coefficient, beta 1, and we're given the standard error. And if you recall a few slides back, to get the t observed or t statistic, all we have to do is divide the coefficient by the standard error, and that would give us our t statistic. Then we would compare that to our critical value and calculate our p-value, and we get 0.001, and 0.001 is less than 0.01. So we would be able to reject the null hypothesis for x1. Let's see. So r squared and adjusted r squared are usually given. So r squared doesn't have as much value in multiple regression because every time you add a new variable to multiple regression, your r squared will go up, so it's inflated. So what we do is we adjust that r squared for each variable that we add. So whenever you're using more than one variable, you should try to interpret, or you should interpret the adjusted r squared. So in this case, it's 51%. So based on these two variables that we've regressed on, we can explain 51% of the variance in this model. But the regular r squared is inflated because we didn't account for the fact that we added that other variable. Let's see. I think that's kind of all the important stuff. So typically, when I look at output, like I highlighted last time, I'm going to look at the adjusted r squared, the p-value for the ANOVA, and the p-values for my coefficients. So if the p-value for the ANOVA is significant to whatever I'm interested in, then I will look at the p-values for my coefficients, and if those are significant, then I will interpret the coefficient for that particular variable. We can see here that x1 is found to be significant, but x2 was found not to be significant. So if we were to interpret that, we would only give an interpretation for x1, whatever that variable happens to be, and we would basically ignore x2 in the sense that there's nothing we can gain from it because, or there's no explanation we can gain from it because that p-value was not significant. And then we would interpret the adjusted r squared that we can explain 51% of the variation in y based on these two variables. Clearly, there's more variables we should be adding and maybe finding a substitute for x2 depending on what the scenario is. Let's see. Okay, so chapter 10, categorical data analysis. I don't have any comics for this particular chapter, but it's still important information to go over. So, multinomial experiment. So when qualitative variable results in one of two responses, it is binomial. So that can be, yes or no, success or failure, favor, do not favor, anything that has a binomial response where it's, on or off, or, there's only two forms. So when a qualitative data can fall into more than one response, it's called multinomial. So in this example, you have some high school, you have finished high school, you have some college, you finished college, or you've gone on to get a graduate degree. So, properties of multinomial experiments. These are kind of the assumptions that need to be met in order to run the chi-squared test we're about to talk about. So, the experiment consists of n identical trials. That's our sample. There are k possible outcomes to each trial. These outcomes are called classes, categories, or cells. Probabilities of the k outcomes denoted by P1 through Pk remain the same from trial to trial. So there's no change. It's like flipping a coin. You know, the first time you flip it, you have a 50-50 chance. Well, the second time you flip it, it still is a 50-50% or 50-50 chance, right? So we're assuming that whatever probabilities that we're working with, they don't change as the trial moves about, which is basically kind of what number 4 is saying. The trials are independent, right? So P1 doesn't affect P2. The random variables of interest are the cell counts, the number of observations that fall into each of those K classes. So our first example, consider the problem of determining the highest level of education attained by each of the n equals 100 salespersons at a large company. Suppose we categorize level of education into one of 5 categories: some high school diploma, some college degree, and graduate degree, and count the number of the 100 salespeople that fall into each category. Is this a multinomial experiment to a reasonable degree of approximation? To answer that question, you just need to identify that it fits into the categories 1 through 5. It's kind of just a question asking for the definition of, is it a multinomial experiment? So, check the 5 properties of a multinomial experiment shown in the box we have. So the experiment consists of n trials. That was the first one. So we had 100 identical trials, where each trial is determine the highest level of education of a salesperson. There are k equals 5 possible outcomes. That's, whether you have some high school diploma, etc. Probabilities of the k equals 5 outcomes. We have, probabilities that remain the same from each, at least to a reasonable degree. Same from trial to trial. The trials are independent, so the educational level obtained by one salesperson has no effect on the education level attained by another salesperson. So we are interested in the count of the number of salespeople who fall into each of the 5 categories. So, what's the sample size of the ones that break down into each of those categories? So, thus the properties of a multinomial experiment are satisfied. So, many weeks ago, we talked about this chi-square distribution. This is where it comes into importance of, we're going to do these contingency tables is based around the chi-squared curve. So in this case, coefficient of friction of desk chair has a chi-squared relationship to productivity. All right, so how do we read a chi-squared? So we're interested in this tail over here of our chi-square curve. And you can see the chi-square kind of looks like a squiggly X. Let's see, I think I have an example for that. So, okay, so we have our chi-square curve, and let's say we wanted to look up, some particular value. If we have k equals 3, so that means we have 3 categories. We have to get, and we want to look at, alpha equals 0.01. You have to do k minus 1 degrees of freedom, and you look up the value of the alpha. So I've given you a function, the chi-inverse function. So if you put in the number of classes you have and your particular alpha value, it'll look up, Excel will look up in the table for you, but you can see that, because it's k minus 1, we have 2 degrees of freedom. We're interested in chi-squared alpha value of 0.01, so that's where we get this value of 9.21034. But since we have Excel, we can use this little formula here to look up values for us. But what it's talking about is the area in this tail here. Okay, so next example is we're going to look at a one-way contingency table. So we have a multinomial experiment with k equals 4 cells and n equals 400 produce the data shown in the one-way table. I'll show you in a second. Do these data provide sufficient evidence to contradict the null hypothesis that each of these probabilities that we assumed they were hold based on alpha equals 0.05. So we can look here. So how do we solve this problem? So we're given a table of some actual measured or sample sizes. So we're given this table here. So we had 4 cells and a sample size of 400. And when we took the measurements, we got these actual proportions. Well, I mean, they're all divided by 400. So we had sample size of 400, and we got these when we measured them. So we want to test these values, or these proportions, to their hypothesized one. So we have, the first one, the null hypothesis was P1 equals 0.02, or 0.2, P2 equals 0.3, P3 equals 0.1, and P4 equals 0.4. So what we need to do before we can run our test is we need to calculate out the what those sample sizes would look like had we run this particular experiment. So we take our hypothesized proportions and we multiply them by 400 to get the values. So what this one-way contingency table is going to test simultaneously is 72 far enough from 80 to be statistically significant? Is 142 far enough away from 120 to be statistically significant? So it's going to pull all those values in, and we do that with a chi-square test. So you can see we have a chi-square.test, and you pull in these 2 arrays. So they're arrays because we're only looking at one-dimensional data right now. But so we have basically the array of our proposed values versus our hypothesized proportions that we expected. So we run that, and then we get our chi-square value, which is 0.09. But what we need is, well, that's the p-value. The problem with the Excel is it gives you the p-value for the chi-squared test, but it doesn't give you the actual chi-squared value. But anyways, we get the p-value here is 0.09. 0.09 is greater than 0.05, so we would fail to reject the null hypothesis in this instance. To get the chi-square value, we use chi-square inverse, right-tailed, and so it takes that p-value that we got, and then we know that it's k minus 1 degrees of freedom, right? So there was 4 minus 1 is 3. And that's how you would get the chi-square value for a one-way contingency table. All right, so do another example. We have a multinomial experiment with k equals 4 cells and a sample size of 198 produce this data. So we have ni, this is our observed values. So we got 36, 42, 58, 62. And our null hypothesis or proposed is we expected that all the proportions would be 0.25. So, and then the alternative is that at least one of those proportions is wrong. So let's look at our experiment. Which one is that? It's 4, right? Okay. So 10.4. So this calculator for, so we have the values that we were given, our null hypothesis, and we're told we need to construct 90% confidence interval. So all I did was, well, for cell 3. So I flipped this data around to make it easier to work with. So we have our sample size for cell 1 was 36, and the proposed value was 25 or 0.25, right? So we remember our sample size was 198. So what we have to do is multiply that times 198, and we were expecting 49.5 the value would be for each of these cells, but this is what we actually got observed. So you'll see, just like in the previous example, when we run the chi-squared test, against these two arrays, we get 0.02. So if that was all we were interested in, we would that 0.02 is less than 0.05 or even 0.1, so we would reject the null hypothesis in that case. We use that p-value and the chi-square inverse right-tailed test. Remember, k minus 1, because we have 4 cells, is 3. And our p-value, it will give us our chi-square value. For constructing a 90% confidence interval, we were given that value, right? So 58 divided by 198 gives us 0.2929, etc. The 1.65, that is the special t number that we need for 90%. And then we have our value with our standard error, and we multiply that out. So this is the complement of that. That's what we need to calculate out. And then we get our confidence interval that we expect the value for cell 3 to be between 0.240 and 0.346. So when you use this calculator, all you need to change is these values here. But that's for a one-way contingency table. See how much. Okay, so a little more calculating a chi-square test in Excel for a two-way contingency table. So now instead of just one level, like, going to college or going to high school, now let's add in another dimension, basically. So now we're going to have a matrix instead of an array. So we have gender and whether or not they agree or disagree or they don't care about gender inequality in the workplace. So we want to find out, basically, is there gender inequality in the workplace based on a survey of 162 men and women? And this is kind of what they kind of voted. So I want to use a chi-square test to determine if there's adequate support of perceptions of gender inequality. So kind of odd distribution. Men seem to agree. Women seem to be equally distributed between them, with more women disagreeing than men. So does our sample hold up based on what we would expect? So what we need to do is rows and columns and find the expected outcomes. Then we're going to run our chi-square test and interpret. So that's discrepancy of different one. All right. So this value. So we're given this value, right? These are all we were given from our given data. And so we have 162, and let's see what it gives us. Oops. So we sum those values because those are the values we're going to need to run our chi-square test. So the sum of the rows, and the sum of the columns, and the total values. It adds up to 162, which is where this value came from. So that adds up. What we want is to calculate out what we expected based on that. So to get those values, to get for men that agree, to get that, we take the total of this row and this column, and we divide by the total. And then we'll get, the expected proportion. So we expected 45 men to agree, but in our actual sample size, we got 58. So the same thing for the neutral. We take the the total value for min, and we multiply it by our neutral row, and we divide by the total, and that's how we get that value. And then same thing here. Multiply our total times our total that disagree, and divide by our total sample size. So that will give us our expected matrix, and this is our observed matrix. So then we use those values or those matrices to compare these two. We run the chi-square test, and it'll give us the p-value. It's very, very low, 0.000003 is very significant. So we wanted to look at our chi distribution, and then to get our chi-square value of 9.2 using chi-inverse. So p-value for if we're doing a hypothesis test, and if we're interested in the actual chi-square value, that's what the chi-square statistic would be. Okay, so based on that, we can reject the null hypothesis because 0.003 is less than 0.5. Okay, so that's contingency tables and how you can deal with qualitative variables using a statistical test. Let's see, we got